Good afternoon, everyone. Today we're going to do an example factoring a quartic function and then sketching graphs with the x and y intercepts. So, first off, we have f of x being equal to x to the 4 plus x to the 3 minus so on and so forth. So, first off, we need to use the rational root theorem to decide what are the potential factors of our f of x polynomial. So, we know that potential, let's say eventual roots first, are factors of the constant term divided by factors of the leading coefficient, which is simply 1 in this case. And so factors of 12 are positive or negative 1, positive or negative 2, 3, 4, 6, and finally 12. And conveniently enough, over the factors of the leading coefficients, which are positive or negative 1. So now we can start off with the easiest to deal with candidates, right? And let's hope for the best and see if we get one of them to work out. So let's try the easiest one of all. If x is equal to 1 as a root, then we plug in x equal to 1 because we know by the linear theorem that any root of our function f of x, when we plug in the value of the root in for x, we will get a value of 0, right? F of a, if a is a root, will be 0. I'll even write that out. If p of a is equal to 0, then a is a root of f of x, and if a is a root, then x minus a is a factor of f of x. And so we can go ahead and test out which of these values when we plug into x are going to give us an f of x value of 0. So let's try 1 for the easiest one. We'll have 1 to the 4, which is 1, plus 1 minus 13 times 1, which is minus 13. So we have 2 minus 13, which is negative 11. Minus 25, which is negative 36, minus, yeah, that's not going to work at all. Let's go ahead and try, let's write it out, it'll be a bit harder. Let's try maybe a is equal to negative 1, just to see. So if a is equal to negative 1, we're going to try f of negative 1 and see if that gives us a value of 0. So plugging in negative 1 in for x, we're going to have negative 1 to the 4 plus negative 1 cubed minus 13 times negative 1 squared. Minus 25 times negative 1, minus 12. Negative 1 to the 4 is 1, plus negative 1 cubed is negative 1, those cancel out. Minus 13 times negative 1 squared is 1, so that's negative 13. Minus 25 times negative 1, that becomes plus 25, and minus 12. And the 1s are going to cancel out. Negative 13 plus 25 is 12. Minus 12 indeed gives us a value of 0. That means that negative 1 is a root, which means that x plus 1, always changing the sign when you go from the root to the linear factor that we get from it, always changing the sign. So x plus 1 is a factor. Now, let's go ahead and divide f of x by the factor that we just obtained to get the quotient, which is the remaining part of the polynomial. We'll have to further factor to get all the x-intercepts, all the roots to come out. So let's go ahead and do that. I'll use synthetic division just to save your space. So if our root is negative 1, we're going to have negative 1, we'll do our plus. Our coefficients are 1, 1, negative 13, negative 25, and negative 12. Let's go ahead and run through this process. So the 1 is going to come down to start it off. Negative 1 times 1 is negative 1. 1 plus negative 1 is 0. Negative 1 times 0 is 0. Negative 13 plus 0 is negative 13. Negative 1 times negative 13 is 13. Negative 25 plus 13 is negative 12. Negative 1 times negative 12 is positive 12. And finally, negative 12 plus 12 is 0. That's a remainder, which is perfect because we know that we only have a root if we have a nice remainder of 0, because that is also what it means for x plus 1 to be a factor of f of x. Being a factor of something means that it divides evenly through it, which means that it leaves a remainder of 0. And so we know we're on the right track so far, and these numbers give the coefficients of q of x, or the quotient of x after we divide it through by our x plus 1 factor. And so now we can write that, it's right here. So far we have f of x is equal to the factor x plus 1 that we just divided through by times this stuff. So we'll have 1x cubed plus 0x squared, right? Let's not forget that coefficient of 0, minus 13x minus 12, okay? And now we can go ahead and try again. Now, we could keep going with this process of trying out different roots, plugging them into the x portion of x, and seeing when we get a value of 0, and finding our roots that way. If you do want to do it that way, you always have the option to do so. I'm going to go ahead and do it with an easier polynomial, because since we already have one factor, we have only cubic left to deal with, which is a little bit easier, but it's the exact same idea. So the potential roots of this cubic are, well, our constant term is still negative 12, like it was before, and our leading coefficient is still 1. So in fact, our potential roots are exactly the same as f of x was. Now we're dealing with just a quotient of dividing f of x by x plus 1, but turns out we're in the exact same spot in that sense. So let's try something out. Which roots look like they might work? Well, at face value, we have a coefficient of 1, negative 15, negative 12. We might have another factor of x plus 1. Let's go ahead and try that. I'll use a different colored marker for contrast. Let's try a is equal to negative 1 again. Now, if I use positive 1, it will say that it won't work because 1 cubed is 1, so it would be 1 minus 13, which is negative 12, minus another 12 would be negative 24. So a equals positive 1 won't work, but a equals negative 1 might, because then we would have, plugging in negative 1 in to x in our cubic function here, we would have negative 1 cubed minus 13 times negative 1 minus 12, which becomes negative 1 minus 13 times negative 1 becomes plus 13 minus 12, and we do, in fact, get a nice value of 0, which means that this means that x plus 1 is a factor, again, which means that it's a double root in our function on our graph. So it'll be a root in multiplicity 2 when comes the time for graphing our function. So let's go ahead and now do synthetic division again, right? Our root is yet again negative 1. Okay, sorry for this mess here. Let's plug in negative 1 again. Addition, multiplication, and now our coefficients are, let's be careful, 1, 0, negative 13, negative 12. With synthetic division, be very mindful to not forget the coefficient of 0. And now let's restart that process. So the 1 up front, the leading coefficient drops down, and negative 1 times 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is 1. Negative 13 plus 1 is negative 12. Negative 1 times negative 12 is positive 12, and negative 12 plus 12 again gives us a remainder of 0, which is a great sign that we're on the right track, because again, if a factor is indeed a factor of the function that it's dividing through, and it should give a nice remainder of 0, and these should be coefficients of the resulting quotient function. And so now, you see we only have 3 terms, and so this tells us that we only have a quadratic left to deal with. And so now, we know that this portion here is going to write itself as x plus 1, because again, we get another factor of x plus 1 times, these become the coefficients of our quadratic, so we get x squared minus x minus 12, And now we're getting really close to being done factoring through. And we still have, let's not forget our x plus 1 factor out front for our original f of x function. So now let's put these together. So we have f of x is equal to x plus 1, and we're going to get that factor twice because we've already dealt with it 2 times, and so that's x plus 1 all squared times what we have left here is x squared minus x minus 12. 12, right? And then hopefully you have a good amount of experience factoring quadratics because at this point, this should be the point, this should be the part of the solution that is fairly straightforward, that is fairly trivial. So let's go ahead and factor a quadratic by thinking of 2 numbers that multiply to make negative 12 and what's the word I'm looking for? And simultaneously add to make negative 1, right? Multiply negative 12, add to make negative 1, and those 2 numbers are negative 4 and positive 3. So that means x minus 4, x plus 3, and now we have a fully factored form for our original function f of x as x plus 1 all squared times x minus 4 times x plus 3. So now we can look for our x and our y intercepts, so we're able to roughly sketch it on a graph over here. So we have, first off, a double root at x equals, always changing the sign from the factors to the roots. So the factor is x plus 1. Our root is therefore at x equals negative 1. And then we have roots at just normal single roots at x equals positive 4. And finally at x equals negative 3. And we also can readily find our y-intercept. Our y-intercept is found by plugging in x equals 0. And if we do that, this is a very convenient form to have a x in if we're going to calculate the y-intercept quickly. If we plug in x equals 0, f of x is going to quickly become 0 plus 1 squared. Again, replacing x with the value of 0 means that we get 1 squared, 0 minus 4 is negative 4, and 0 plus 3 is 3. And so, I should say not f of x, but if we're letting x take on the value of 0, let's say f of 0, that's a better way of saying it. F of 0 is 1 squared, which is just 1, times negative 4 times positive 3, which gives a value of negative 12 for f of 0, which means that our y-intercept is at 0, negative 12, which is a really nice starting point. Let's draw that name down here. Again, let's label the coordinates to make it nice and readable. Now, what we have here is a positive leading coefficient, even degree polynomial, right? Degree 4 on this quartic. And so we know that the end behavior, we know that its end behavior is going to look roughly like a quadratic because any even degree positive leading coefficient polynomial acts roughly the same at the very ends of its graph. And so we know the end behaviors are going to be Q2 over to Q1, right? Starting high and ending high on the other side. Now we have a double root at x equals negative 1. We have a root at negative 3 as well. And we have a root at positive 4. Again, this is a very rough sketch. I'm just making it look somewhat accurate so that we're able to sketch it with a little bit of precision, but don't spend too much time making that perfect. We just want a rough sketch that we're able to get the rough gist of it. So now we know the graph is going to start high because the end behavior is Q2 to Q1, so it's going to start in Q2. Now it crosses the x-axis at x equals negative 3 because that's a single root. Then a double root at x equals negative 1 means it's not going to go through. A double root means it's going to turn around and go back down, right? And then It's going to turn around at some point. It's going to cross the y-intercept, and it's going to turn around and go through the root at x equals positive 4 to finish off going upwards over in quadrant 1. So putting that all together is going to look like we're going to cross, again, starting in quadrant 2, starting high. We're going to cross over at -3. And then we're going to have a double root at x equals -1. Then we're going to shoot down our y-intercept. We're going to have some vertex down there. We have no idea where that is, but that's okay. And then we know we have to end up shooting off in quadrant 1, and we have to go through our single root at x equals positive 4. And so let's cross that one more time. And we trail off in the positive direction in both x and y. And so that is a very rough sketch of our f(x) function with our x-intercepts and y-intercepts labeled. If you want to get the full coordinates, that's -3, and -1, 0, 4, 0, because that's what we kind of wrote down for the y-intercept. So, putting that all together, we have f of x in factored form, we have a rough sketch of x, we have the end behavior described explicitly. I hope this makes sense. I hope this was helpful. If you guys have any questions, comments, suggestions, please do leave a comment below, and have a great day.